Okay, so it is my great pleasure to introduce Professor Anne Broadbent from University of Ottawa. So now she is a full professor at the University of Ottawa, Department of Mathematics and Statistics, with close appointment to the Department of Physics and to the School of Electrical Engineering and Computer Science. Professor Broadbent holds a University of Ottawa Research Chair in Quantum Information and Cryptography. Her research relates to cryptography, communication, and information processing in quantum world. So he got a PhD from Université de Montréal under Gilles Brassard and Alan Tapp. Her research is very well recognized by multiple award and including the University of Ottawa Young Researcher of the Year Award, the Ontario Early Research Award, and the Andre Eisenstadt Prize in Mathematics. So her research is mainly quantum cryptography, and so to me, she has two very important achievements. So first, a great achievement is a blind quantum computation nowadays, which is known as BFK protocol. And this is a first protocol, secure protocol for delegation quantum computation. And this nicely used as the idea of measurement-based quantum computation. And because of this, this BFK protocol gets much attention, not only in cryptography, but also condensed matter physics and other fields in quantum information. And also, her recent second very great achievement is a certified deletion. This is some quantum cryptographic primitive where you can show that some quantum data is deleted. And of course, this is impossible in classically, but if you use quantum physics, you can achieve this. And this is a very breakthrough result. And nowadays, many classical cryptographers are interested in this research. And now we have very many papers about this subject. So now, today, she's going to talk about quantum unclonability. So please start.
Thank you. Is this microphone? Oh, okay. Okay, thank you very much for the introduction. It's really a pleasure to be here and to visit Kyoto for the first time and to meet the many talented people here. I'm very excited to tell you about quantum unclonability in a colloquium style. I'll give you a background, tell you about the big questions in the area, some of the solutions that are arriving from my research group and from others. I don't know why that popped up. Oh, maybe everybody sees this. Okay, maybe I'll leave it like that. So feel free to ask any questions, and if there's a Zoom host, feel free to speak up and let me know if there's anything happening on the Zoom. And welcome to the people in Zoom. There's the camera, I think. Okay, does this work? My battery died. Okay, so the starting point is this fundamental principle. You can call it a theorem. I'll describe this a little bit mathematically shortly. The concept that quantum states can't be copied. So if you're, well, this audience is probably all familiar with quantum mechanics. This is a theorem at the intersection of quantum information and quantum physics. Basically, if you're giving a single particle of an unknown preparation, it's impossible to create two identical copies. So for me, quantum information is much more like a physical object. So if I tell you you can't copy an apple, that is really obvious. Of course, this is a physical object. We cannot copy it. And that intuition is completely different from the conventional case for classical information. So let's look at the distinctions. So if you have a piece of fruit, like an apple, you can sample the apple, get some information about it. Like you can taste the apple, but that leaves a trace. The apple is irreversibly changed. The apple can be shared. You can distribute the apple among many parties, but each party will have a slice and not the full piece of fruit. And kind of related to that, you can't copy the apple. That's very different from conventional information. Classical information, like our digital communications network, where information is encoded in binary digits called bits, and completely different. So you can observe the information without changing it. And actually this Zoom session is taking advantage of this. Everybody is receiving the same digital signal, and the fact that they're receiving it doesn't limit what the other people are seeing. You can share the information at will. Indeed, we're broadcasting this seminar right now, and also related, you can copy conventional information. So if you're looking at the current information theory, it's really on this side. If you add quantum, you're on this side, and there's a really big separation here because of the no cloning principle. I want to give you a little bit of the mathematical formalism for those who haven't seen it, so that we'll be able to state and even prove the no cloning theorem. It's a really basic linear algebra concept. So qubits are the fundamental unit of processing for quantum information, Q for quantum bit, and the basic states are vectors in complex vectors. Actually, and in of length 1. So that represents a general quantum state. And systems are combined with the tensor product. So if you have multiple qubits, the dimension of a 2-qubit state is a vector, a 4-dimensional vector, complex vector, and we'll use the shorthand notation of this. It's called the tensor product, this operation. Shorthand will just skip the symbol and even skip the distinction between these notations for the yeah, no, I'll use this. Actually, this has, just let me test it. Oh, yeah, it has this type of pointer. Advantage is that people on Zoom can also see the pointer. So measurements will convert qubits to bits, so convert classical quantum information to classical information. These are also called observables. So how do we observe a quantum system? It's via this measurement process. So a single qubit will be, when it's measured, you'll observe 0 of probability, norm of alpha squared, and 1 of probability, norm of beta squared. So simple example, and this actually also has some really interesting consequences to quantum cryptography, which is the topic that we're going to get to today. So if you have a single qubit state, this is called a superposition of equal superposition of 0 and 1, and you measure it, you'll observe 0. The postulates of quantum mechanics, these are linear operations, and that means that we can use matrix multiplication for representing the transformations on qubits. And in fact, if we want to maintain, we need to maintain this norm 1 property, and the family of matrices called unitary matrices are exactly the ones that have that property. They preserve Euclidean norm. So we also have a nice characterization of the unitaries, namely that if you take the complex conjugate transpose and multiply by U, you should get the identity. This is an if and only if. Okay, so that was a little bit of the formalism so that I can state this no cloning theorem. So the no cloning theorem, once more, says that there's no way to take a general quantum state and make 2 perfect copies of it. Okay, so the theorem says there's no 2-qubit unitaries exist that will, for all single qubit states, will take input copy psi, a workspace, and will output 2 perfect copies of the state. And this is fun because you can teach this to first-year undergraduate students who were just learning linear algebra. And basically, the theorem follows by a really simple contradiction. So suppose such a cloning unitary exists. So you will be able to clone a general state alpha 0 plus beta 1. And so you'll get 2 copies. And if you expand that, you get this algebraic representation. And you could also clone this basis state 0 and 1. And this gives these equations. And then by linearity, if you apply this same hypothetical U, you'll get a different expression, this right-hand side. You get a different right-hand side for the same left-hand side. And so this is a contradiction. Meaning that such a U does not exist. Okay, so we have this no cloning principle, and let me see. I'm on a mission to understand how that no cloning principle has implications, and even what is unclonability. So trying to understand this basic principle, we don't have an answer to that question of what is unclonability. What we do have is different representations of unclonability, different situations where we observe things that, thanks to quantum mechanics, and we have the impression, thanks to the no cloning, are possible in these different settings. And my picture is specifically in terms of cryptography, and I'll say why in a second. Such questions were kind of started in 2009 by Scott Aronson, where he discussed things about the potential of quantum copy protection and links to quantum money. And we'll get to quantum money soon. So the approach that I'm taking to understand unclonability is closely inspired by historical developments in cryptography. Cryptography is the art and science of secure communication systems and computation systems, and it has at least 20 years of advanced over quantum cryptography. They having the benefit, of course, of many more years for developments. And there was a really interesting point in time in the 1980s where the community was a little bit of a standstill. They needed to understand, what does security mean in order to be able to continue and to formally analyze encryption schemes. This was the beginning of public key cryptography, and that was really a revolution. And on the theoretical side, they needed a good model to be able to study these principles. And this work on probabilistic encryption by Goldwasser and McHelly was really very important in that development. They managed to describe what security would mean for an encryption scheme. And when you think about it, if you're trying to come up with your own definition in your office, you'll run into many problems. You'll be like, oh, well, what if the adversary has prior information about the message? Then we should say that the encryption does not allow increased information about the message. But then what is information? And then you get into so many situations that are difficult. They gave a very simple definition that covers all those situations. And I'm not going to go into the details of what it is. Basically, they defined a game, and security of an encryption is based on the security of that game. So it's an adversarial situation, which is very appropriate for cryptography because there's always an adversary trying to eavesdrop. And so that's my approach to understand unclonability from the point of view of some sort of games and trying to find these basic principles. Now, this is a historical overview of concepts on unclonability. The quantum money is a really interesting situation. This was a very, very early work in quantum information by Stephen Wiesner. It was written approximately at the end of the 60s. This was before the word qubit existed. This was before no cloning principle existed. This was possibly the first information processing use of quantum, period. It was so much ahead of its time that it was not well recognized, and Wiesner had a hard time publishing it, so much that when it got rejected, he kind of put the project aside. And the abstract, I'm not going to read it in details, but basically the abstract talks about the uncertainty principle. So this is the Heisenberg uncertainty principle in quantum mechanics about the these inequalities in terms of complementary quantities. And he also introduces a novel form of coding. So we'll talk about that a little bit. It took until 1983 to publish this work. In fact, this was published almost at the same time or just before a quantum key distribution protocol was published. And there's definitely a link between those dates. I'll tell you about that soon. So what did Wiesner do? He proposed what is called today what he called also conjugate coding. And in conjugate coding, there is a basis, theta, and a bit r. And these two are combined into a single quantum state, r sub theta, that is, that is a Hadamard of r. Okay, good thing I have this table because I haven't told you what Hadamard is. So let's rely on this table to understand between theta and r. So theta can be the basis 0. And when r is 0, the encoding will be ket 0. So this is the basis vector 1, 0. And when theta is still 0, but the bit is 1, then we encode in the orthogonal state ket 1. And when the basis is 1, we will be encoding with a diagonal basis. So the 0 will be encoded as ket plus, which is this equal superposition of 0 and 1 written down here. And the 1 will be encoded as ket minus, which is this equal superposition. And the really interesting thing here is that theta, depending on the basis theta, we could, if we know the basis theta, we could know what the bit r is. Okay, and we can even verify. So if somebody receives one of these 4 conjugate coding states and knows r and theta, then they can verify that that state is intact by measuring in that basis theta. Intuitively, there's, however, a limitation on copying one of these conjugate coding states. So if a recipient receives one of these 4 without knowing which one, then there's a limitation on how well they could, that person could create 2 copies of the quantum state, both of which would pass the verification mentioned here. Both of which would pass this verification. And that was kind of the extent that Wiesner expressed it. Much later, we had formal proofs for this, this situation. So if we do conjugate coding n times in parallel, so we'll have n of these quantum states, then that is the banknote that Wiesner had envisaged. Namely, we have, so he was thinking about photons as the quantum information carrier, where the polarization would correspond to the basis. So you could have maybe a horizontal, rectilinear, which is horizontal vertical for theta equals 0, and diagonal, which is diagonal right, and diagonal left for theta equals 1. So already at that time, and still today, we don't necessarily recommend investing into quantum money because we know that photons and their polarization will almost instantaneously decohere and they'll lose their value. We do, however, know that that this scheme is secure. And at the time of Wiesner, this was the security argument. So he talked about the difficulty of duplicating and copies of copies. It's really interesting to see in those days what was kind of the type of security argument. Nowadays, we have much more formal definitions and proofs. But really, he was already pointing to this concept that the unclonability of quantum would be at the underlying phenomena that made this quantum money unclonable. Okay, so formally, and getting back to this idea that in order to understand unclonability, we'll formulate types of games and understand their possibilities and impossibilities. So formally, we have a one quantum state, an adversary Eve that's trying to forge, it's trying to take one piece of money and create two pieces of money, both of which would be accepted by the verification procedure. Okay, so you take one, the adversary takes one, tries to make two, both of which would accept. So the question is, how does the difficulty of winning this cloning game? So we want to post-select on the situation that both of these quantum monies are going to be accepted by the bank, for instance, where the bank also knows the preparation of the quantum money. And it turns out that the probability that the money is accepted at both locations scales as 3/4 to the n, where n is the number of qubits. And this was obtained by using semi-definite programming by Molina, Vidic, and Watrous in 2012. So interestingly, it took many, many years to get to the formal statement and proof of the optimal counterfeiting attacks on Wiesner's quantum money. Since then, there's been lots of work on quantum money, and there are really interesting questions, some of which have been addressed. So we're trying to look for short-term or near-term implementations that would also be secure and tolerant to current technology. So a noise-tolerant quantum money. That noise-tolerant will accept the quantum money will be accepted even if it's slightly noisy. And there are schemes that use classical verification only. And there's also a really rich area called public key quantum money. And in this situation, any user in the network can verify the quantum money. Notice that so far, the quantum money is verified only by the emitter because they need to know the basis theta. So in public key quantum money, anybody, including maybe a merchant, can verify that the money is intact, and yet having access to the verification does not allow to break the scheme, of course. So this was started about 12 years ago, and research on this topic still continues with some of the most pressing questions, namely even the possibility or concrete schemes for public key quantum money. And there's at least one central bank government that in Sweden actually that's looking into quantum money as a future technology. Quantum money has really nice. It's a really nice concept to study the unclonability. It doesn't encode any data. It's like a coin, for instance, where you can verify that the coin is authentic. Data itself it's another level of information because it has meaningful interpretation. So a bit string is a data, a name of a person, a password, etc., are all things that are not necessarily covered by quantum money. But maybe if we go to some other level of information, maybe we could use the no cloning principle to get something interesting. And this story goes back many, many years to 1979, where at the time, early career computer scientist at Université de Montréal, Gilles Brassard, met Charles Bennett, at the time a physicist at IBM in New York, and they were literally swimming in the ocean off the coast of Puerto Rico when they encountered each other. And Charles Bennett goes up to Gilles Brassard and says, hey, I know a way to make unclonable quantum money. Let's talk. I know that you're a cryptographer. Let's talk. And the story is that Charles Bennett was acquainted with Stephen Wiesner. They had been friends, or they were friends, and they had in particular interacted quite a bit at the time that Wiesner was working on his manuscript on quantum money. So he knew about Stephen Wiesner's work and was on a mission to make it more widely known and more applicable. And Gilles Brassard was a cryptographer, classical cryptographer at the time. And they were at a conference together, and Charles Bennett had noticed that Gilles Brassard was going to talk about cryptography. And indeed, this was a very important encounter because they together conceived of this idea of quantum key distribution. So this is taking the idea of conjugate coding and making it into a cryptography system for communicating private messages. And today it's called BB84 quantum key distribution after the authors Bennett and Brassard. Some of you may have heard about quantum key distribution. I don't necessarily want to go into the details. In fact, I'll show you a cartoon image of the protocol that's maybe the simplest that you've ever seen, but I think it goes straight to the concepts of the quantum concepts that makes this work. So the situation in quantum key distribution is that Alice and Bob are separated. They can communicate via quantum, and there's potentially an adversary on the line. And they want to be able to share a secret key in the sense that Alice will know the key, Bob will know the key, and the adversary in the middle will not know the key. And once you share a secret key, that's sufficient for secure communication via XORing or doing some bit manipulation between the message and the key, and using the key only once. Okay, so Alice has a key that she would like to transmit to Bob. If she sends the key on the channel, Eve will see it, and this will compromise the security. So what she does in this cartoon scheme is she hides the key in an apple. Okay, and she sends the apple over to Bob. The apple, of course, is a metaphor for the quantum encoding. The key is now encoded into a quantum state. Bob receives the apple and removes the wrapping outside and is able to extract the classical key. Of course, I'm skipping some details, not telling you exactly how this works. The principle is that when there's an adversary on the line here, and the adversary actively interferes and is trying to gain information about the apple by sampling it, for instance, then this is detectable by Bob. So the apple has been transformed by the adversary. So in that case, Bob will know that there's been an attack on the line and can notify Alice that they should start over. This key is insecure. Okay, that's my really short version of BB84. The implementation uses the idea of conjugate coding, and that's going to be used to detect eavesdropping, as we've seen. And the concept is that if there's no eavesdropping detected, then the shared key will be completely secret, and this is impossible to achieve. Classically, we can show that. So this is really an advantage of quantum communication for secure communications. And ever since then, we've been working on trying to find other areas where quantum communication provides some advantages. And now we get into much more recent work. So now we're thinking about quantum encodings for classical messages. So this envelope represents a classical message, and that it has some version of a quantum encoding. And we want to use the no cloning principle to fundamentally limit the way that copies can happen here. I wanted to mention that this no cloning principle has been in the past equated to a difficulty of quantum information. So at the beginning of quantum computing, people were saying, well, there's a really big problem. There's this no cloning principle, and that means that we won't be able to use error correcting techniques. So error correcting techniques are required in faulty environments, and quantum computers are notoriously faulty, or quantum transmissions are notoriously faulty. And the basic principle of error correction for classical information is to use duplication. If we send a message and duplicate it multiple times, then that's resistant to interference via the majority type of decoding. And that means that because of no cloning, this approach is completely unavailable. So that was brought up as limitations. For me, as a cryptographer, the quantum no cloning is a great great resource because it's also a limitation on what the attacker can do, or what an adversary can do. They're also limited by the no cloning principle. So where some people see a disadvantage in no cloning, I see the bright side. Okay, so that's the way that these ideas of certified deletion and unclonable encryption are two projects that I did with graduate students. And that's what we're going to talk about now. And these are related to the thinking about quantum information as physical objects. Okay, so in the introduction, we heard a little bit about this idea of certified deletion. I would like to tell you what it is. So it's a physical type of encryption. Alice is going to take a message, and in this physical world, she would hide the message into a safe. Okay, so imagine that you have this large safe, or not even large, a safe, and you write down the message, you put it in the safe, and you close the door. And you randomize the lock. Okay, so she'll send the safe to Bob. In this case, Bob now has this physical object in the safe, and he has two possibilities. He could take the safe and give it back to Alice. And that when he returns the safe to Alice, Alice will then know that he's never been able to read the message, namely because the safe has stayed closed, the combination is hidden, and she has this physical object in her hands, so she knows that Bob has never read it. He could, on the other hand, keep the safe on his side, and eventually the combination will be available. This could be by design, or maybe eventually the encryption key is leaked by some process. And once he gets the combination, he can open the safe and read it. And between these two options, there is an XOR, okay, an exclusive OR. Bob can do this one or this one, but not both, okay, because there's only one physical safe. He can return it or keep it. And we would like to know, can we achieve this type of functionality in the digital world? So could he really provably return the safe to Alice or not? Digital means a classical encoding. And that's the situation where we don't have the no cloning principle. When we don't have the no cloning principle, it's easy to see that this type of safe analogy is impossible to achieve. Here, Alice encodes a message using a key and sends it to Bob. Now, Bob has that message. It's a classical string. He can make two copies of it very easily. And that means that he can use the first copy, for instance, to convince Alice that it's a basic argument by contradiction. He could use the first copy to convince that he's returned the message, and use the second copy to open and read the contents. So what happened here is that because of cloning, he has two copies, and he can do these two behaviors. In the work on quantum encryption with certified deletion with Rabib Islam, we showed that really using quantum mechanics, you can achieve in a cryptographic situation the best of the physical world, where objects are unique and unclonable, and the digital worlds where encodings are digital and you can process them using computers. So we're going to encrypt a classical message into a quantum state. And then Bob can prove that he deleted the message by sending Alice a classical string. So this is even more than returning the safe, if you like. It's creating a proof that the safe has been destroyed. And as an application of this certified deletion, imagine that you have your last will and testament. So this is what you leave to your heirs in case you die. You leave that last will and testament with the lawyer's office. And this can contain some very private information. So suppose that you leave that your will with your lawyer. And a few years later, your life situation completely changes. And you go back to the lawyer and said, oh, please, you need to delete that. I don't want anybody to ever see that will. And here's my new will. So if you had encoded with a certified deletion, the lawyer could indeed certify that the will in any of its possible copies has been completely erased. There's no way that anybody in the future would be able to read those intentions that you had, say, 5 years ago. And you can, of course, replace it with your new version of your will. So that's what quantum can offer us. And I want to give you a basic idea of how it works. It uses conjugate coding, and it uses complementarity or uncertainty relations. So if you wanted to encode, this is an example where you want to encode 2 bits of a message. Your message has 2 bits. The encoding is going to use 4 qubits. So each column here is how you prepare your 4-qubit message. You'll choose a random basis, a random R, just as we've seen before. Apply the Wiesner encoding that we've seen before. You have, this creates 2 substrings. R subcomp is the qubits that are encoded in the computational basis, and R diag are the qubits encoded in the diagonal basis. So if your message is 2 bits, the encrypted version will be the 4 Wiesner conjugate coding states, as well as the message binary XOR, which is the sum modulo 2, with RComp. So RComp is 2 bits, and you basically apply what's called the classical one-time pad. You encrypt the message M using RComp, which is a substring of R. There are 2 complementary actions that we would want to do given the ciphertext. Bob could want to delete the message, which is related to returning the safe. So to delete the message, Bob would measure all the qubits in the diagonal basis. And when you measure the qubits in the diagonal basis, the ones that were encoded in the diagonal basis have deterministic outcomes. Namely, you should that substring should be consistent with R diag. Okay, so these stars are wildcards. They can be anything, and the 1 and 0 are deterministic. And if the string has this form, then Alice accepts that the message has been indeed deleted. And this is the verification procedure that I just mentioned. On the other situation where Bob decides to keep the safe, well, in order to decrypt, you would simply consider the key theta, which gives you the basis, and measure all the qubits in the position where theta is 0 to get R comp. And this substring is exactly what's used to encrypt and also to decrypt and get the message M. Okay, so that's how we are able to have these 2 complementary actions, deletion and decryption. The intuition of the proof is that the adversary can do anything, and that's what makes these proofs very difficult. So we don't know exactly what they'll be doing, but we can still bound some quantities. And this is a trade-off between how the probability that Alice is going to accept and a proof of deletion, and the probability that Bob would be able to decrypt given the key theta. And I just want to give you an idea of the concept, basically using these uncertainty relations that are formally the entropic uncertainty relations. In this version by Masson and Ufink, we're kind of trading off the uncertainty on one variable X with the uncertainty of one variable Z, and the C is the overlap between the observables. So you have this lower bound, and this translates for certified deletion into something like the probability of guessing R comp correctly decreases as the probability of predicting R diag, which is related to being accepted in the certified deletion. So certified deletion has seen a lot of follow-up work, including some at Kyoto University, and things like making the protocols device independent, making the keys reusable for higher functionalities, something called fully homomorphic encryption, and for also cryptographic primitives such as commitment and zero knowledge proofs. Okay. So I'll go into a second example of encoding classical information into quantum information and some advantages we can get cryptographically based on the no cloning. And this is unclonable encryption. So thinking about an encryption scheme, if Alice has a message and she wants to encrypt it with a key K, this is the ciphertext. And suppose she sends the ciphertext and that's intercepted by a pirate. Then the pirate can make 2 copies of the ciphertext and send them to other friends, Bob and Charlie, let's say. Suppose that at a later time, the key is revealed. So by design or maybe by some security flaw, the key is actually made available. Well, in the case of classical encryptions, then it's obvious that both of these parties, Bob and Charlie, given the ciphertext and the key, are able to decrypt. Okay, that in fact is the correctness of the scheme. If you know the key, have the ciphertext, you should be able to decrypt and get the original message. So both parties are really able to get the message when they get the key. Okay, and I should say that there's no communication between Bob and Charlie here after they've received the message from the pirate. Now, when you know about the no cloning principle, it's a very natural question to say, okay, well, what about the no cloning principle? Could we use quantum mechanics to limit the possibilities that parties B and C would have to simultaneously decrypt given the key? And so thinking about the type of security game you would have, so this is the picture that we've seen with an abstract encryption scheme. Would it be possible that the limitation on the encryption is that the probability that they're both able to know that both Bob and Charlie output a message that is equal to the original input message? So if the original input message is uniform, that's what the symbol means. Could we bound that and say that it's no larger that basically 1/2 plus a small function that grows exponentially quickly in the security parameter? So 1/2 to the n corresponds to a simultaneous guess that would, they could do that without even having help of the pirate. And we could hope that quantum mechanics could enable this. So far, this hasn't been achieved directly. In the original work that introduced this unclonable encryption, we were able to bound to this probability with a constant factor 9. And I'm not sure if I have a slide, but we also assumed some extra assumption called an oracle. So why would you want to use unclonable encryption? Here's an application, and it has to do with copy protecting digital objects such as movies. So and think about the release dates of movies. So suppose that there are many movie cinemas and there's a featured movie that's being distributed, and you want to make sure that the cinemas are not duplicating and sharing their copies of the movies before the release date. So this could be encrypted using unclonable cryptography. And at the release date, then the key will be revealed and the projection rooms can decrypt and show the movie. And however, before the release date, there's a fundamental limitation on how this movie could be shared. So here's the scheme that we had. It also uses conjugate coding. And to encrypt a message M, we'll prepare n conjugate coding states. And we'll, similarly as the certified deletion, send those conjugate coding states together with the message one-time padded with this random R. And this is this modulo 2 addition. So we'll send that. And if this is the picture of the pirate, say the pirate tries to distribute to Bob and Charlie. Eventually, Bob and Charlie would get the key K. The key K here is this basis theta. And the question is, how well can Bob and Charlie simultaneously guess this message M? Fortunately, this scenario has already been studied, and we picture it as in an alternative picture called the purified or entanglement-based scheme. We picture instead that the pirate prepares a row ABC, a joint quantum state. and distributes it to Alice, Bob, and Charlie. And then Alice will measure in a basis of her choice to obtain the string R. Theta is revealed to Bob and Charlie, and the question is, how well can Bob and Charlie simultaneously guess the measurement outcome of A? Turns out that bounding this winning probability corresponds to a bound on the original game for unclonable encryption. And this specific situation has been studied by Tomichel, Fair, Kanuski, and Vayner in what they called a monogamy of entanglement game. So this is a mathematical concept that's very relevant for unclonable encryption. And they showed that the optimal winning probability is a half plus 1/2 to the power n, where we have n qubits in the encoding. And this is pretty good for us. This would scale as 1/2 to the n times 1/2 to the n. Oops. And that's what we used to plus a random oracle, which I'm going to skip for now, to get this unclonable encryption. There's still a very interesting and important open question in unclonable encryption, and that's to achieve something of a higher security level. And this would be the game. And an open question is, could we do the following? Alice is going to encode a single bit and send it to the pirate, etc., as usual. And we would hope here that we could bound the probability of winning to be very close to a half. So the previous work on unclonable encryption does not imply this because we encrypted longer messages. And so open question, and please remove this n. And so the open question is, could we get such an expression for a specific encoding scheme, ENC? And this is a very important step towards a higher level of security called unclonable indistinguishability. I think I'll stop there. So there's another hierarchy, there's another level of information which is functionality, like software, circuits, computations. And there is quite a bit of work on making such software unclonable. And I'll happy to take some questions if you like, but in the interest of time, I'll skip to the conclusion. So really, the quantum unclonability is inspired by the physical world, about objects, about things that are really that we conceptualize as being unclonable, and then we managed to find digital versions thanks to quantum encodings. So we've talked about unclonable money, certified deletion, unclonable software, which we skipped over. And really, I would challenge people to look at what else can we make unclonable, and that would help us understand this larger picture of what is unclonability. Thank you very much.
Thank you very much. Any question or comment?
Interesting. So I'd like to ask whether, so assume that, for example, Bob says he still doesn't use that key, but just send it back to Alice, but he actually uses it, but he just claims that it is just contaminated by error when sending back to that message to Alice. Is it possible, for example, statistically to discriminate that situation?
Thanks for the question. Was this for certified deletion, maybe, like this thing about returning? Yeah. So it's a good point that you can say, well, what if there's noise on the system and we would like to be able to still be resilient to this noise phenomena, meaning that even if Bob returns the safe, but it's not a perfect copy of, it's not a perfect version of the safe, and it's not his fault, okay, because the channel was noisy. Could we still get a type of certified deletion? And fortunately, even in the original work with Islam, we were able to show that the scheme is noise tolerant in principle, okay, the actual thresholds and making it more and more noise tolerant is still an open question. And the way we were able to do this is by using techniques that were really well developed in quantum key distribution. So that's been a very important question since the beginning. Could we still establish a shared secret key even if there's non-malicious noise? So thanks for the question.
I have a basic question about your quantum unclonability. So in quantum mechanics, of course, we cannot make a clone. It's just, we cannot make a copy of the single quantum system. But your case have some very small probability that, your enemy can create copy, exponentially small. I think you write it 2 to the nth power. How this small probability comes?
Okay, thanks. Okay, impossibility of cloning is a little bit of a imprecise statement. So I admit that I've been a little bit imprecise. If you're really wanting to go to the point of, well, what does it mean to clone? So the mathematics says you can't make 2 copies. And I could also mention that there's a lot of work on optimal cloning, which is approximate cloning, et cetera. And those things are possible. There's also possibility of approximate. So the approximations are always poor, but you can do some versions. For instance, the maximally mixed state is an approximate cloning. It's just really bad. Okay, so for instance, if you have, and the classical equivalent of this is that somebody sends a message, you don't know what it is, you can still, with probability exponentially small, guess, and you'll have a copy of it. Okay, so that's 1/2 to the n. So that's the 1/2 to the n that is kind of carried through all the calculations.
I see. Thank you very much. Very clear.
I'm curious about this unclonable software or copy protection for like DRM stuff, right? And I can kind of figure out if the system is always online, then I can totally see a way to do this. But if kind of like what are the limitations on the adversary that force it to, once the software is being unlocked, to kind of not be able to just copy it as is and distribute copies? Because in the end, you still need the software itself to be classical, right?
Oh, not exactly. Interesting point. So we would like in unclonable software to have offline digital rights management, basically, so that the software is available, a single honest user can use it. Yet a single honest user cannot pirate it, really, in the sense that pirating is currently understood, so that 2 remote parties could simultaneously use it, all offline. And in that case, it means that the software itself is never actually made into a classical version, so that when say I encode the software, give it to you, you would, in order to evaluate it, you'll do something that's natively quantum, and that does not open up the entire source code. Okay, so right now, the state of the art is certain functionalities, certain security models, certain security definitions. Actually, there's way too many ways that you could define and implement unclonable functionality, and people are exploring that right now.
Okay, thank you. Because that's what I'm interested in, like having a classical program that has some part of it being quantum. But
yeah, that's what. Yeah, so I've done some stuff. This is some of the work. The list is not comprehensive, so I've done some of this work here on copy protecting point functions. Point functions, you can see them as password verification situations. So there's a single point that evaluates to 1, and otherwise all the inputs evaluate to 0. And we encode that point into a quantum state, and one single honest user will be able to evaluate using this. Using our concept. It's related to quantum method authentication codes. And our model is honest malicious, related to one of the evaluating devices after the pirating, following the honest evaluation procedure. and the other evaluation device following some pirated version of the evaluation procedure. And we're able to show that you can copy protect point functions in that case.
I'll take a look at that paper.
Yeah.
Thank you.
Yeah.
Any other question?
Thanks for a great talk. So I would like to ask a very fundamental question. So as you may know, no cloning theorem holds in every convex physical theory or any generalized probabilistic theory. Then, so it is not specific to quantum theory. So then my question is, what do you think is specific to quantum unclonability or quantum cryptography? Is there any candidate for you?
Oh, so yeah, as a cryptographer, I'll take that as an opportunity to maybe go into some unclonable functionalities for generalized probability distributions, which also have a no cloning principle. That's what you're saying, right? That's pretty much as I could say. It sounds like an interesting avenue.
Any other question?
At the back.
Thank you for a very nice talk. Yeah, I wanted to ask about this part in which you mentioned about the connection between the connection to entropic uncertainty relations. Is it the case that this connection that you mentioned is something very special, or is it perhaps, can we hope perhaps to find additional or perhaps more general connections to, because, well, as far as I understand, there is a whole world of uncertainty relations. So,
oh, you know a lot about entropic uncertainty relations. We should discuss. Okay, because it's very, very useful. So definitely. So what we linked is in our proof of certified deletion, we linked work on quantum key distribution. Security proofs for quantum key distribution, which is a very large area, and one of the approaches to security for quantum key distribution is these entropic uncertainty relations. And so we found a link between the certified deletion and quantum key distribution, and therefore we're able to use I think there was an entropic uncertainty relation from Thomas Michel, if I'm not mistaken. These are at the okay, so the no cloning theorem is never actually used as a proof, so nobody ever actually uses it. It's a concept, the principle. When you go and use and want to observe no cloning, then you go into much more subtle security proofs, and the entropic uncertainty relation is one of those. So for me, uncertainty is an embodiment of unclonability. The versions that we used were particularly useful. They had the exact same situation of n qubits and these two complementary quantities. And what they bound is the probability of being able to predict the outcome of a hypothetical measurement of one observable and of the other observable, which is based on the inner product between the two. So definitely advances in entropic uncertainty relations would directly translate to advances in understanding unclonability.
Other question or comment? Is there any question online? So what is unclonable indistinguishability? So you slightly mentioned.
Yes. Okay. So thanks for the question. I only really glossed over it. Unclonable indistinguishability. This is the version of the game that we were able to prove something. So it's not satisfactory from the cryptographic point of view of security of an encryption scheme. It's more of a demonstration that the principle is possible. And the thing is that here the message is uniform. And the probability is that both parties are able to guess the exact same message in terms of an n-bit string. And remember when I talked about the semantic security and one of the revolutions in conventional cryptography, they would not be happy with this. Okay, so they would say this is not the most strict definition of encryption. The unclonable indistinguishability replaces this by a single bit and allows the encryption into a larger string, and then asks how well could they both guess that single bit. And the point of the the unclonable indistinguishability is yeah, so it's a full message of n bits, and Alice is going to encrypt that full message or a random message. And then the challenge is for Bob and Charlie not to know the whole message, but to know what was Alice's choice. Did they encrypt the entire message, or did she encrypt that random message? So their output is a single bit, and optimally, we would like to show that the best probability corresponds to probability a half. So that was a little bit quick, but there's a lot more discussion of this open question in this 2002 paper, which really looks at some approaches, but it's still an open question to have a statistical security game. And the reason I presented the bit version is that I consider this a building block. If we can prove the bit version, I think we can scale it up to the n-bit message version.
So at this moment, there is no security proof for this indistinguishability.
There's no security proof in the statistical plane model. So there are versions that are computationally secure and random oracle.
Also, do you assume that adversary can query encryption oracle or decryption?
That's a good point. In conventional indistinguishability, they can query the encryption oracle, and yeah, I think I would add that to be that would be ideal.
Any other question or comment? Any question from Zoom? Okay, so if not, let's thank the speaker again. Thank you very much for very, very clear and insightful talk.
Thanks for coming.
Thank you.